In this lecture, we talk about a very important lemma which will be used in the proof of Noetherian normalization theorem. So we start with some polynomial f in k x1, x2 all the way to xt comma t. So in this polynomial ring. Then for a suitable m which is a natural number, we do some transformation of f. So we write it as x1 plus t to the power of m comma x2 plus t to the power of m square, then x3 plus t to the power of m cubed all the way to xt plus t to the power m d comma t. So all this is important. It will be clear in the proof why we are taking such powers. So such a transformed polynomial actually will take this form: lambda times t to the r plus c1 times t to the r minus 1 all the way to cr. Now all these c1, c2, c3, they could lie in this polynomial ring from k x1 all the way to xt. This t we are taking out like this, but this lambda lies in the units of k. So you can actually factor this out to get a monic polynomial, and this is the monic polynomial which will be precisely used in the Noetherian normalization theorem. So this monic polynomial will set it equal to 0, and then you can take this lambda common out because it's a unit, and therefore you get a monic polynomial to satisfy some integral equation. So let us start with the proof of this theorem. So say our polynomial is given like this: x1, x2, xt, t, and then it is summation, then there are some coefficients, and then you have x1 to the power of j1 all the way to xt to the power of jd and t to the power of jn. So now you can see the degree of any one particular term is just our summation of all these ji's. So that will give you a particular degree of a particular term. So there could be many terms with the same degree, and that we have to resolve somehow later on. So now we choose m as maximum of all these j1 to jd. So because this is a polynomial, so there are only finite number of terms, so we can talk about all these different tuples of j1 to jn, and then you take m as maximum of all of them. Then you take xi and transform this xi to xi plus tmi. So just focus on this part for a minute. So every term will have this thing. So this thing will transform into this. So x1 becomes x1 plus t to the power of m j1, then x2 will become x2 plus tm square j2, and this xt becomes xt plus tm to the d jd. So this jd is coming right here, this j1 is coming right here. Here we are not doing anything and just copying it as such right here. So notice that how we have changed the variable. So now this m is maximum of everything here, and so this is m to the I. So now if you expand it, you will have t mji. This will come from here. Then from the second term will come m square j2. From here will come m to the power of t jd, and this jn will come right here. So this jn comes right here, and this is going to be the highest degree precisely because we have chosen m to be greater than j1, j2 all the way to jd. So this x1 will have maximum power of j1, but this m is anyway greater than it, so you have this maximum degree term. And then we have lower degree terms in both in t and xi, but this is the maximum degree. So this is going to be the maximum degree for every such term. So this polynomial will have sum of terms. For every term you will get a t which will have the maximum degree. Now I'm put a dangerous bend symbol here because each of the exponents like this are distinct, since they are distinct base m expansions. And why we need this is because there could be two terms which have the same degree. So for example, if you have some term like this 1 1 1 and the rest of the things are 0 0 0, so this has degree 3. So say this j1 all the way to jd, and then forget about jn, but for these three terms you have degree 3, and then you could have 1 0 1 0 1 and rest of them are 0. This could also have degree 3. So how do we distinguish between these two, because these two elements are having the same degree? And to do that, precisely that's why we have taken m to the power of I, because now although they have the same degree, we have the expansion in terms of this mj1 plus m square j2. So this will be 1j1. This will be just m. This term would be m square, and then third term would be m cube, and everything would be 0. And similarly for here. But now this is different base m expansion, this is different base m expansion, although they have the same degree. So we can distinguish two different degrees together. And a term like this will obviously give us a higher degree than this because of this ordering. And in some other proofs, there is a lexicographic ordering also given. Essentially the same idea, because we want a term with the highest degree. So now all of these terms, because this polynomial is made up of some finite terms, each of the term will give you something maximal degree like this. So for all these terms, which are all finite terms, because polynomial is always made up of finite terms, you choose n to be the biggest such exponent. So then you can write f of x1 plus tm x2 tm squares this comma t. So that is after change of variable, you can write it as lambda times t1n, because the coefficient of this is just this c, which is nothing but so this c has to be non-zero. This is obviously in the units of k. So the coefficient of the highest term is always non-zero, and you just take the maximum of that. It will have some lambda which will be in units of k. But all other coefficients, lower terms in t, will also have xi's in them. So this c1, c2, this c1 tn minus 1 all the way down, each of these ci's could lie in this. But we were interested in having this lambda being a unit.